Hello, so today we are going to do this problem, which is part of Leetcode Daily Challenge, water bottles. So basically here we have a number of bottles initially. They are all full. So for example, here we have 9 initially full. And then you can exchange a certain number of empty water once you drink the water from the full ones with one full water bottle. So for example, here you could exchange 3 empty water bottles with one full. So what that means is you have initially full water bottles. So let's say you drink 3, now they are empty, then you can exchange them with one full bottle. Okay. So basically, when you drink full water bottle, it becomes an empty bottle, of course. And then once you have the number of exchange of them, you can exchange it with one full one. Now, the goal of the problem is we get both the number of existing initial full bottles and the value to exchange with, the exchange value, and then we want to return the maximum number of water bottles you can drink at the end, all the way to the end. So if we take a look at the first example, we start out with 9 full, right? And then you drink 3, you drink all of them, right? So, and then exchange number is 3, so that means for each 3 empty, you get one full. And so, because we have 9 that turn into empty, each 3 turn into full, so we have 3 full ones. We drink those again, we have, since it's just 3, we get only 1. And then when we drink that one, we have 1, we can't exchange it, so we are done here. Okay? Now, how many water bottles, full water bottles, did we drink? We have 9 at the beginning, we have 3 here, and then we have 1 here. So overall, 12 and then 13. Okay, so that's the value here. So that's the rough idea. Okay, so how do we do this? If you look at the constraint, the values are pretty small. So that tells you we can do a simulation pretty much. Basically do exactly what's being done here in the description. So how do we do that? Well, first we can just we know what we need to return at the end, which is the count of what we drink. So let's just define that here. Initially, we definitely drink the first full ones. And so that's just the initial number of bottles. This is what we need to return at the end. But we also need to keep track of the empty ones so we can know how many full ones we get. So let's just have... so after the first operation is done, we drink, let's call this drink, we drink number of bottles and they become empty, right? So this is basically initially after first drink operation, okay? Now, what happens? Well, when are we done? Right? We are done when there are no longer enough empty bottles to exchange. Like here, we have 1, but we need 3. If we have 2, we still need 3, so we can. But if we have 3 empty bottles, like here, we can exchange those with 1. So we are done only if empty is no longer bigger or equal to the number of exchange, right? Now, this is a drink operation, right? Plus exchange with empty bottles. Okay, so first we need to know, so first exchange, so 1, exchange empty bottles with full ones, okay? And then the second part is to drink the full ones, right? So for the first part, how do we do it? Well, for the first part, we need to know how many we can exchange, right? So full, let's call them full exchange. It's going to be the number of empty ones. Like here, for example, we had 9. How many we can exchange it with? Well, it's 9 divided by 3. That will tell us, because each 3 will give us a full bottle. This will give us 3. So that's exactly what we are going to do here. We know this is how many full we can exchange. Okay? Now, let's say let's say for the sake of argument, let's say maybe this was 12. Let's say there was another bottle and then another bottle here. And so now we have empty. So we can exchange the 9 here with 3 full ones, but these two will remain here because there is no way for us to exchange them because we need 3. And so we need to keep track of these two because we have these 3, we drink them, we have 3 empty ones, we will have 5 now, okay? So we need to keep track of these. So that means empty, how many remaining? Well, empty is going to be this full exchange one, but whatever is remaining of this division, which is just empty modulo the number of change, okay? And we can do this, simplify this like this, okay? That's just the remaining after the division, the ones we couldn't exchange because they were below the number of exchange value, okay? Okay, so now we need to drink the full ones. So drinking them means we add them to our drink counter. So we drink these, and these become empty once we drink them. So once we drink them, they become empty. For exchange, bottles become empty. And so we need to add them to our empty counter, right? And that's pretty much it, right? Just doing exactly what we did. So in this specific case, in the first iteration here, what happens is we drink, we say we have 9 empty, right? And so this will give us 3. So we have 3 full bottles. That's what we have here. And then how many empty remaining? Well, empty modulo 3, which is 9 modulo 3, is going to give us 0. Okay, so that makes sense. So we increment our drink value here was the number of 4 bottles, so 9. And so we add the full ones, which is 3. So now it's 12. And then we add the full ones, which is 3, to the empty. So now empty is, the value is 3. So this is here, what we have here. And then we go again, empty 3 is still bigger or equal to 3. And so again, how many we have for exchange? 3 divided by 3, we have 1. And that's exactly what we have here. And then for the empty, which is 3 modulo 3, 0. So still 0. And then we drink the 1 that we have here. So now we have 13. And then empty, we add just 1. Now we have 1 empty. But then when we come back here, 1 is smaller than 3, so we exit the loop and we return 13, which is exactly what we have here. Okay? So that's the logic for the solution. Now let's just run it, make sure it works. Submit. It should get accepted. Just taking a little bit longer. Yeah, so that gets accepted. It passes. Okay, so now what is the time and space complexity for this solution? Well, first let's do the space complexity because it's easy. The space complexity here, you can see we are using only variables, so definitely of 1 space. But what about the time complexity? Well, that's a little bit harder to do with this loop here. But the main thing is when we are trying to find the time complexity for a loop like this is to find the number of iteration. How many times does the while loop run? And here we know that it will, let's call it k iterations. Let's call it that it runs for k iteration. We are trying to evaluate roughly how much is this k value. Okay. Now we know that on every operation in this while loop, right, every iteration, well, empty becomes just the empty value, the previous empty value, modulo the number exchange plus this, the full exchange, which is this. Okay, right, because we add that at the end here. So this is sort of the rate of change for empty. Now, if you look at this, ignoring the modulo because that's usually a small value, each time it gets divided by the number of exchange. Now, for the sake of just example, what if number of exchange was 2? Then this would be modulo 2. This would be divided by 2. Right? So what would that be? This would be either 0 or 1 because it's either odd or even. But this will half empty on each iteration. So if number of exchange was 2, then you can see this is of log n, right? Log base 2 of empty, right? And empty initially we initialize it to number of bottles, so this is actually of like of a number of bottles, right? So you can see already there is a log involved, and it's of the number of bottles, and here it's base 2 because number of exchange is equal to 2. So coincidentally, this is also the same thing for if you do. If we just replace 2 with number of exchange, then it's of log base 2 of num of exchange of number of bottles. This is the number of iteration it runs on. So this is roughly the time complexity. I think you could do something more precise here, but I think this should be good enough for the time complexity. Okay. Okay, so now let's think about if we can do better than this time complexity. Can we do just O of 1 operation? Can we do just O of 1 time complexity? Well, let's think about this for a minute. Well, we know what we are looking for is the number of bottles we drink. We definitely know that we first drink the initial bottles plus something, plus some value. This value is basically x is going to be turning number of cycles, right? Because we turn into empty from this, and then we get full replacements. Then we turn those full replacement into empty. Then we keep going. Number of full water bottles on multiple cycles of drinking, turning into empty, and then exchanging with full. Okay. So how do we determine this x? That's the tricky part. If we can determine that x in some sort of formula, that will solve the problem, right? Now think about this. If you have 3 empty, you get 1 full. So you actually lost 2 bottles, right? You actually lost, so every time you reduce by number of exchange minus 1. You reduce what you have by number of exchange, because the number of exchange turns into 1 full. So let's say number of exchange was 5, then you will turn that 5 into 1. So how many did you lose? 4, right? Now, initially you had, so what this tells you is basically to know how many full bottles we will get to be able to drink, we can divide whatever we have as here, we can divide it by this, because this is what will tell us how many full bottles we'll get, because each time we reduce the empty bottles we have by this, right? Because 1 we will get as full and the rest will go away, okay? So that will determine how many we will have. Will go away because we exchange it, okay? So what's this number? Well, it's actually just the initial number of bottles minus 1, okay? Now the question is, why minus 1? Well, again, same reason, because we exchange that full we will get back that 4 bottles every iteration, right? So we only need to divide by this, and so this is actually the x value that we are looking for, and so we can just return this like this. Okay, and if we run this, let's see, let's submit, and it passes. And this is O of one time and O of one space. Yeah, so that's pretty much it for this problem. Thanks for watching, and see you on the next one. Bye.